Let me just introduce you a little bit. So Anima, as you may have read, is the Bren Professor of Computing at the California Institute of Technology. She was previously Senior Director of Machine Learning at NVIDIA and Principal Scientist at Amazon Web Services. She's a pioneer in using AI for science, and her research considers tensor algebraic methods, deep learning, and non-convex problems. She's going to give a short 20-minute or so talk, and then we'll have a fireside chat and hear all your questions. Welcome, Anima.
Thank you. Thank you. Thank you, Eric. And let me try to move this closer. And okay. So, I'm sure all of you are thinking a lot about generative AI one way or the other. I just heard about the use of AI tools. So, you're very much aware of the language models, but I do think there is a revolution, not just with language, but the use of these kind of frameworks of learning broad generative, models in a distributional sense that also has an impact in many scientific domains. Indeed, just to kind of quickly set the stage, why generative AI and what's so great about it, right? The hard part is to be able to generate samples of some high dimensional distribution. What that means is very complex aspects like, of course, large pieces of text, images, but also molecules, proteins, maybe new genomes of mutations of coronavirus. So you can think of like this ability to not just reason about a given input, but to generate new samples. And that's really the difference. The previous era of AI over the last decade was more about discriminative AI. I give an image, I ask you what's in an image. That's discriminative because you're trying to understand, okay, this image is more of a cat and not of a dog, right? So you're making those distinctions. And a lot of what we did until these language models came about was to focus more on being able to discriminate within given samples in an accurate way. But of course, with enough compute, it turns out that generative AI is possible, right? It's really the process of going from a specification that is low dimensional, meaning a simple prompt or a simple wish list of what you want in a molecule, to the actual molecule, which is, of course, in a much larger set of possibilities. That's a hard process. So you're going from a simple specification to an output that is much more complex. But with enough data and scale, we are able to accomplish that now. Of course, just to, again, very quickly set the stage for language models, the idea is very simple, right? The way we train language models is to predict what the next word is given all this context. So you just learn how to predict this well at scale, what we call pre-training, and then you give a little bit of human feedback, what we call the alignment process, which is done with reinforcement learning, so it's RLHF. And with that, you make the models able to understand our prompts or our instructions so that they can respond in an appropriate way. And at the same time, of course, try to make the model not spit out hate speech or anything that is bad in many ways. So the process itself is very simple, right? So it's all focused on getting as much data as possible, in fact, internet scale data, and then learning to predict the next word. And then from just that very simple aspect of looking at what is the likelihood of different words that would appear given the current part of the sentence, you're learning the underlying meaning in a certain way. Like you understand how words appear in different contexts by learning this at scale. So of course, language by itself is great for a number of applications, but not all of them. And ultimately, what language lacks by itself is embodiment. Right? So you can learn how different pieces of text are related to one another, what is the underlying meaning of words. But words need to translate into actions, when it interacts with the physical world. And that's where we need an agent or an embodied agent, where you take, like instructions in text or interact with text in a certain way, but ultimately convert them into actions. And so this is one of the early work we did at NVIDIA, where we, in fact, in collaborations with also many folks here at Stanford, where the idea was to give instructions in text about what objects to pick and place. So you see a mix of image and text as instructions, and have this ability now for the robot to execute a whole range of different tasks, right? So text is a nice way to provide now the ability for robots to be generalists, meaning not just be trained to do one specific kind of task or pick only one specific set of objects, but now in a zero-shot way, generalize to new ones. And it need not be just in the physical world, it can also be in virtual worlds. The Voyager work we did was to show how you can use language models to now continuously learn skills in a variety of environments, including Minecraft. So you can progressively learn skills from simple to complex, and also use the skills you learned beforehand. This is how we humans do, right? So we pick up certain topics, and as a curriculum, we go and tackle harder and harder problems. And that's what we taught our agent to do, to use language models as a way to come up with actions that you can execute in Minecraft, but also decide what to do next. And this is where it's different from standardly reinforcement learning. When AlphaGo beat the world's best Go champion about a decade ago, right, that was very surprising that AI could really be able to, go through so many possible moves and pick out optimal moves that were better than the human. But then it was focused on just one game and one task. So the goal was just to win, right? So that was already predefined. Whereas in Minecraft, I don't know how many of you have played Minecraft, it's about creativity. You don't just focus on one thing, right? You can go build these castles that you're seeing. I think somebody has even built a CPU and GPU in Minecraft. So it's endless what you can do. And that's where I think the promise of AI agents is. So language models are not just in isolation, but they can be used by these agents to continuously query and get help. But ultimately, those agents are figuring out how to continue to gather skills and solve increasingly harder problems in environments. And the Minecraft is really a showcase of that. You can think of the same for software applications, for all kinds of software programming. And you're seeing that I think it just goes off to sleep if I, we'll see. So, the one thing that still lacks if you only do language models is the aspect of dealing with hallucinations. So these models currently are not grounded in facts. Of course, if you train on all of the internet, everything is mixed together, right? There are people telling jokes, poetry, to software code, to mathematical facts. And now if you're asking language models to prove theorems, you cannot expect it to be 100% correct. It can claim that this is the correct proof, and many times GPT can be wrong. And instead, what we did in this project, and that was one of the suggested reading that I had given, was to now add with language models that ability to verify whether the statements the language models are making are correct or not. And this one we don't need to build. There's decades of work called formal verifiers or formal theorem provers. And lean is one of the leading ones. There are many, but there are, for several reasons, many mathematicians, including Terry Tao, who's one of the leading mathematicians, they use lean. And there's a large community building this formalization of math into lean. So what that really means is if you go read a math paper and you look at all the proofs, you don't know if it's correct or not. Like you, as an expert mathematician, may go and try to be like, okay, this one's correct, this one's correct. But instead, if you had a program that could certify that every step is correct, then you kind of, first of all, don't need to worry about the correctness of proofs. But ultimately, the same concept is useful in a wide variety of areas, especially safety critical areas. A lot of the control of, let's say, aircrafts or drones, rockets, is done with the same notion of formal verification. So every step of the program, you have to certify to be correct. Otherwise, it's just too unsafe to use programs without that correctness. And we can do the same in terms of using Lean, but combine it together with language models. So language models now propose ideas. Language model can say, oh, I think to prove this GCD, which is the greatest common denominator, which again, you don't need to know the specific notations in the proof steps. Language model can say, oh, this is what I think the next step in the proof is. And then Lean as a verifier can certify whether the step is correct or not. And so this way, anything that is proven by the language model is now 100% accurate. So there's no hallucination, right? And you can do this in math because you can correctly verify and certify every step. And in other areas, not so much. If you're talking about social beliefs or moral issues, you cannot say, okay, this step in the logical reasoning is correct, and that's why let me go to the next step. But with math, we can do that, and that's where I think, domain-specific applications of language models can be done better, right? You can remove hallucinations in many areas, and specifically if you can have verification like in math, you can 100% remove those hallucinations. So I think that kind of logical reasoning is really important ultimately for AI to succeed in many of scientific domains. And so, so far I talked about how language models could be used in a range of different applications. But you can also change from language to other modalities, other kinds of data. And one of the such areas was using now genomic data instead of English language or any natural language. So what that entails is now you have sequences of nucleotides, right? The ATGC, if you remember the DNA. And then now you can give these sequences and again, ask the now genomic language model to learn to predict the next set of nucleotides in the sequence. And what this does is learn the underlying intuition of what genes do. What is the functionality of different genes? In the same way, what is the meaning of underlying words in natural language? So it's the same analogy that holds. And again, we do this at scale. We did the first genomic language model where we trained it on more than 110 million genomic sequences of many known virus and bacteria. So this is the UK Biobank. It has the biggest collection of known mutations of viruses and bacteria. So everything from flu virus, E. coli, coronavirus. So everything you can think of, we collected all of them. And again, the difference is if you're asking a biologist, they're usually studying one specific virus, right? They're looking at flu, they're looking at, how could it mutate? The CDC is trying to come up with some best guesses of what would be the best mutations and then creating vaccines to target those mutations. But now with the use of these large-scale generative AI models, you can now look at how are all of these different virus and bacteria evolving over time. Because you're learning across all mutations, you can figure out which ones are more likely to happen than others, and hence coming up with a way to predict new variants of concern. And that's what we did, where we fine-tuned the model just to focus on coronavirus. So during training, we showed it the variants that appeared just in the first year of the pandemic, which was alpha and beta variants, right? So the other ones hadn't yet appeared, but the language model trained on genomes accurately predicted the variants that emerged later, like Delta and Omicron. So what the model is able to do is successfully learn the evolutionary dynamics of how viruses are likely to mutate. And this is very helpful for us to get a hold on all the latest pandemics. I mean, we haven't done the bird flu, but I imagine that'll also give us interesting insights.
Can I ask a question?
Sure.
Yeah, so that's amazing. So were they able to make vaccines in advance, or is that the idea that you would have a vaccine before the variant even appears?
Yeah, exactly. That's the idea. I mean, by the time we were training this already, the Delta and Omicron waves had just kind of passed, right? So for this pandemic, it was a bit late, but
and then
hopefully
once
for the
you
next
do it, you
two.
can also start predicting what some of the characteristics are, or is that beyond what you guys are doing?
And precisely the next question, right? So you can now produce these genomic sequences, but what is the impact? I mean, which ones are more concerning than others? Which one should be
Like
worried
a certain set of base pairs might lead to a more lethal.
Exactly.
Yeah.
But how do you study that? And to do that, in this example, what I'm showing you is how does the spike protein of the coronavirus, which is in blue, interact with the protein targets in the human body? So you need to understand where is the binding strong and where is it weak. So if a strain is much more lethal or more concerning, it tends to bind stronger. And that's when it's more disruptive in the human body, right? So just by looking at the genomic sequence, you cannot gather all the information of which variants should we be worried about. On the other hand, if you now go into the details of the biological process itself, what does the virus do? How does it go into the human body and bind with protein targets inside the body, as well as other aspects too. We studied. We looked at, how does it get transmitted in the respiratory aerosol? What are the molecules it binds within a respiratory aerosol that makes it infectious, right? You transmit through that. And also, how well does it replicate, and what kind of factors help or hurt the replication process of this virus? And so this is where, to study all this, you cannot just look at discrete data or a sequence kind of data. I made this analogy that genomes are just like language. Instead of the English language with 26 alphabets, you have only 4 alphabets, which is ATGC, and you have that sequence, and you learn a model in a similar architecture, use transformers, just as you did with language. But now to study these kind of processes, which is now in space and time. So in space, you're looking at what are the binding, which molecules bind with each other, and also how does this molecular dynamics itself change over time. And these kind of processes are just, abound in nature. You can start from all the way at atomic and molecular level to planetary scales. So in the second example of planetary scales, you can think of what is the weather going to be tomorrow? Will there be storms? Will there be rain? And for that, you're looking at processes that involve everything from, what are the particles within a cloud that cause precipitation, to these very large-scale effects like atmospheric rivers, which are important for California because that's what causes storms in winter, and they can be thousands of miles wide. So you have from microscopic to macroscopic phenomena that are all interacting together to cause the weather on this planet. And that's the aspect where, just language models by themselves will not be enough, right? Like language is a high-level description of certain phenomena, just as math is a high-level description. You can, in fact, describe these processes through mathematical equations. So if you're looking at molecular dynamics, you can use Newton's laws of motion to describe how the molecule will be stretching and moving. You can also go down to the quantum effects and use Schrodinger's equation and all of its approximations. So if we perfectly know the equations that describe these systems, but what's challenging is the ability to simulate it at scale. In fact, to do that for quantum simulation, you would be needing more than the the computation would take more than the age of the universe, even to simulate just a molecule with 100 atoms. So that's the bottleneck, right? So here we are in a different regime compared to language models, where with language, it's very difficult to try to describe the rules. There are too many exceptions. There's not just a mathematical equation to describe all of English text, right? On the other hand, we have lots of data on the internet, and we're learning from that. But on the other hand, if you want to try and learn these kind of physical phenomena, the data is limited. There's certainly some observational data. You can go and look at these viruses and under a microscope try to look at what is happening with these protein interactions. You can go, of course, with satellite data, right, try to assess what is the kind of wind and other patterns happening in our atmosphere. So you can get some amount of data, but it's limited. And now the question is there still a notion of generative AI or large-scale AI models, even for scientific phenomena? And the way we can do that is to incorporate this knowledge of mathematical equations. So either we can use existing simulators to generate data, or we can directly try to incorporate the knowledge of physical laws and equations into our models. But the one challenge to do that is this requirement to capture really the fine scales. So if you want to understand how clouds in our atmosphere move, you need to get to these really fine scales. And that's what makes these simulations very expensive if you did that with traditional numerical solvers. So for instance, if you have to simulate clouds, the resolution you need to get to is of the order of maybe 100 meters or so, which is, even within Stanford campus, you need multiple grid points, lots of them. And now think of doing that at a global scale. That's an extremely fine resolution image of the Earth you need to do. And you need to then also do that in time in very fine increments to get accurate simulations. And that's what makes this infeasible when you try to do it with traditional simulation methods. So what traditional simulations try to do is look at equations and try to directly solve them, right? So they're not making use of any learning from data. They're saying, okay, let me try and solve these equations. But to do that, I can only take small steps, and then I need to take a lot of such small steps, which becomes too expensive. And also, if the area itself is large, I need large memory to make the grid fine enough to make this solver converge. And this is where AI now has the potential, not only the potential, now we have the evidence that it can speed up solving these kind of mathematical equations in a much faster way than possible before. So the analogy is similar to what you see with computer vision. Before deep learning, people were hand engineering features, right? So if you had to classify a face, there were certain features which were thought to be better. Yeah. Exactly, like try and look for the eye. So you could go and hand engineer every one of them, but the tail is too long. You can't try and do this for every variation of the face, every angle, every lighting. And same with, in a way, the numerical solvers. You can try and hand engineer the features to try to make it converge, but you don't know if those are the best features. And even though we may require a very fine grid, if we try to directly solve through all of these points, you could find a transformation to a nonlinear transformation to a latent space where the grid is much coarser and you get a speed up. And that's what we did with the use of these techniques called neural operators. So neural operators are extending the notion of neural networks like transformers, but to now continuous spaces. So if you think about now, how I mentioned about clouds, right? So you can try to model the cloud at a certain resolution. So on the right, if I choose my resolution to be too coarse, I get garbage, right? It's too blurry. It's not enough useful information to actually predict how the cloud is going to change over time. And that's the challenge with a lot of the physics, if you don't make your grid fine enough, you will not be able to accurately capture the prediction in terms of how the fluid is going to flow. And this is where it's also different from computer vision, where it's more about visual appearance. If for me, visually it looks good enough, it's good. But that's not so true to get the correct physics in terms of accurately predicting what will happen to fluid flow like clouds. So what we did with neural operators was not to worry about fixing the resolution to just one value. Instead, think of how in graphics, you have vector graphics and you have raster graphics, right? This is the same analogy here. In the raster graphics, you prefix what should be the resolution, what should be the number of pixels. And if you go further zoom in, it just gets blurry because you haven't increased the number of pixels. On the other hand, with vector graphics, you represent the data as shapes, right? You parameterize them as shapes, and you can keep zooming in, and you can still get sharp images, sharp graphics. And the neural operators do the same, but instead you learn what those shapes should be. So you're always representing the output as functions that are continuous. And so you can keep zooming in to any resolution, and it can still give you valid answers. And
so the neural operator learns the functions instead of you programming them.
Yes.
From a neural net, yeah.
From the data. So you can now give it data of fluid dynamics of various scenarios, or you give it weather data, you give it data of how material stretches. So all of this, you don't have to fix beforehand what should be the resolution. And in fact, you can train it on data with multiple resolution.
And a neural net can fit any arbitrary function.
Yes.
So you can make it arbitrarily precise.
Exactly. And you can, so the main difference is in text with transformers, you're learning on discrete tokens. So you fix what is the vocabulary of your language, and you're giving a token for each part of the vocabulary, right? And that's how you get the tokens. On the other hand, here we are not defining the tokens at one resolution. Instead, we are saying these tokens could be infinitely defined into any resolution I want. So we're giving that flexibility. And I won't get into the technical details here, but this is just saying that by doing so and capturing the finer resolution, we can get to the finer scale. So on the right is a plot in terms of like how we are accurately predicting what happens at higher frequencies or finer resolutions, even though the model didn't see that during training.
So how do you define the function? If it depends on something, like how does the function vary?
Yeah, and that's the beauty of it. With these models, you learn them from data. You don't fix them beforehand. So for instance, if I fix the function to be just sine waves, right, like sinusoids, that's what the Fourier transform does. But that's too limiting. If my model is not sparse in terms of sine waves, then I can't accurately represent it.
So is it like inferring the function?
Yes, precisely. It's learning the function itself from data. What should be the function? And it's learning that through these nonlinear transformations in between, just as any neural network does, just as transformer does. And because of that, it's trying to find shortcuts to solve these partial differential equations more efficiently compared to numerical solvers, which are already having a fixed path of how to solve it. Yeah.
So can you sort of think about this as like dimensionality reduction?
Yes.
But like with functions instead of like normal like linears.
Exactly. So what standard neural networks do is do dimensionality reduction, but on a fixed resolution, right? You decide what the resolution is at training time, and at test time, you're forced to be at the same resolution. But now we'll remove that limitation and say the input and output can be given at any resolution, and I can still learn a dimensionality reduction. I think there was a question there, yeah.
For numerical simulation, it seems like the biggest constraint was compute cost. Can you give me a sense for what is the compute improvement by enabling these? I'm sure it's different across disciplines, but like 10 times, 100 times, and then how does that affect this?
A million times.
Is that true? So for weather prediction,
for plasma evolution, it was 1 million times.
Sorry.
Plasma evolution in nuclear fusion.
Okay.
And for weather prediction, it was tens of thousands of times. And so what really determines this is how hard is it for the solver to, the need to get to the finest scales. So something like plasma in a tokamak reactor can become extremely unstable, right? And what scientists need to do is make the grid very, very fine to try and understand when will the plasma suddenly escape confinement and become unstable, cause disruptions. And so the harder the simulation is, think the gains will be much more. Something very simple like pushing a ball, maybe we won't get any speed up because it's so easy to directly just solve it. In closed form, you can tell me what that is, right? There, I don't need this. So think of cases where you need a very fine grid to solve because it's highly unstable or nonlinear, the effects those fine scales have on the broader sense.
So earlier you spoke of how, with regards to mathematical proofs, there's this notion of using verifiers to check the outputs.
Yeah.
Say we're solving some system of PDEs using this neural operator. How are the verifiers kind of extended to this application?
That's great. And that to me is like a world where all of this comes together, right? So the theorem prover is purely symbolic right now in the sense you're looking at what are the variables, you're formalizing those statements, right? And you're proving them step by step. There's no numerical solution. So you're never making the variables into specific values and solving them. On the other hand, this is purely numerical. So right now, if you give me Navier-Stokes for fluid dynamics, I'm just directly trying to solve it. I'm not symbolically manipulating or making any kind of further modifications. But one day, there could be a neurosymbolic method, right, where you try to make valid transformations that make the equation simpler. Maybe not for Navier-Stokes, but especially coupled equations, lots of them, you try to minimize it in a symbolic way, but you also try to numerically solve them better. And right now, the main bottleneck is, these verifiers like lean do not have a lot of good support for calculus or differential equations because, there are like areas like topology where it's purely symbolic, right? And so more of the energy is there. But one day, that would be a way to bring in neurosymbolic approaches to this.
So let's actually have everyone say their name. I think it'd be useful for...
Yes, and maybe some context. Yeah, that would be...
Yes, I guess my question is concretely, what's the difference between the inputs that go into a neural operator versus which go into a classical machine learning framework? At least in vision, you can train a model to work at lower or higher resolutions, but it's still...
Otherwise, it's the same thing. So think of it as a video model, right? It's like Sora or any video model. You can give it space and time. So it can be like a 3 dimensions in space and in time, or 2 dimension in this example. So it's the same approach as in a vision model. The only addition is now the flexibility to directly input multiple resolutions, both at training and testing time.
So then do you have to change anything in terms of the standard layers you use to adapt to different shapes? Or how does that?
So the main change is to make it now flexible in terms of handling these inputs and outputs. So in the middle layers, you can still use a transformer. You can still kind of make it into a coarser grid and use any of the standard approaches. So think of it as mainly at the input and output, you need to make changes. But looking at it in terms of the class of architectures, you can take any of the existing architecture, like a convolutional net, a transformer, and extend it to now handling multiple resolutions. That's essentially what these are doing. So this is not a new architecture in itself, but it's more now a superset of existing class of architectures.
Hi, I'm a PhD student studying formal methods.
Yeah.
And so just coming back to the computational gains you described earlier, you've mentioned that you've described the models that you're using. Can you talk a little bit more about the architecture some more? Like, are these large transformer-based models, or are these results coming from regular, like fully connected networks and stuff like that?
Yeah. So like I mentioned, in the general sense, these neural operators are an extension of any neural network. So you give me a neural net, I can turn it into a neural operator, meaning I can make now the layers of them be able to handle any resolution of input and output. But of course, among them, which one is a good candidate, right? So in this example, what we've done is use Fourier neural operator. So it has Fourier layers, but it also has nonlinear layers like MLP, like even attention layers you can add. So it has a combination of that. And the Fourier tends to be very good for a lot of these applications, especially in fluids, because you have interaction across multiple scales, and that is better described in a Fourier domain. But unlike a traditional method, it's not purely based on Fourier transform, right? You have these nonlinearities in between, and that's how you learn a more expressive basis than purely a Fourier basis.
Could you talk a little bit about how you landed on a Fourier? Like, how did you know that was the architecture you used? Was there some fine-tuning along the way?
So this actually came from our discussions with my collaborators in applied math and those who've been using numerical solvers. And it turns out for fluid dynamics, a popular solver is a pseudospectral solver where you go to the Fourier domain, you make some steps or iterations, you come back to the standard domain, and you go back and forth. And we realized that in between, you could add a lot of nonlinear layers. You could also add nonlinear encoders and decoders. And with that, you make that expressive. So in that sense, a special case of that is still the numerical solver, right? So if those models just learned identity transformations, then you go back to your original solver, which is a valid solution. But you could do something much better than that. And so we came at it while trying to preserve the properties that numerical solvers already have, but extend the expressivity of those models. But it also has a nice connection to transformers and others. So it kind of meets both the traditional simulations and neural nets in a nice way, if that makes sense. That's a quick,
I'm a CS undergrad, and I'm curious about the mechanics of this specific network. So when it outputs, for example, its next frame prediction, does it plug that prediction back into the input to get the next frame, or what are the?
Yeah, again, we have multiple options. That's called autoregressive if you plug it in and do one by one. For something like weather model, that's what we did. But we've also had models where you can roll out in a latent space, so you don't need to do that in the observed domain. We also have models where you directly output, answers at any time step by also having like a Fourier or the other kind of approaches that can do any resolution in time as well. So again, there are many different candidates, and it depends on the use case what would be the most appropriate. Yeah. Great. I know lots of questions. Do keep them coming. So I wanted to just show some of the use cases of where we've used neural operators. The weather model was one of the first complex domain, I would say, where we chose this. So what makes weather challenging is, first of all, it's high resolution. This data is like 25 kilometer spacing across the globe. And we have historical data going back to 4 decades. And it's not a lot of them, about 50,000 samples, which is nothing compared to the language models of the world, right? So it's good amount, but it's
50,000 time stamps? Or,
50,000 like initial condition to next time step. So pairs of data.
And how many, so if it's every 25, how many grids is it?
1,000 something in each, like 1,000 odd, like 1,200 or something, like, or 1,600, I forget. You can do the math globally. So think of that as like the image. It's, for computer vision, it's a fairly high resolution image. But also we don't have a lot of samples. The other thing that makes it challenging is also many channels, right? So unlike RGB for images, you now have wind speed, humidity, you have different layers of the atmosphere. So there are like more than 100 variables. So you have this high dimensional challenge of coming up with the weather. And when we started working on this in the late 2020s, we had come up with neural operators. We wanted challenging use cases. The fluid dynamics was already considered challenging enough, but we wanted to also touch something that directly impacts the real world, right? But many people thought we were crazy. Oh no, this is decades of methods that are developed for forecasting weather. And I do remember growing up and thinking, one of the use cases for supercomputers was always I was told that, oh, look at weather models, weather forecasting, that needs a big supercomputer. And so our question was, how much can we do well with respect to using neural operators and a completely deep learning based method? Meaning I take my initial condition now and I use now a neural operator to predict the next the time step, like the weather at the, say, in 6-hour increments. And we do this autoregressively, and we can give like 2-week forecasts based on these predictions. And it turns out that it is much faster. The first run of the model, it was about 45,000 times faster than what you can do with numerical models. So literally what would take this big supercomputer based on CPUs, you can run this on a local gaming PC. So all you need is a consumer grade GPU, and the model is open source too. So you can download the model and run your own weather model. We've open sourced it with permissive license. And I think that to me is what shows the promise and the ability of these models to really miniaturize what is considered as very complex physical calculations and do pretty well. This model is also running in ECMWF, so you can go get real-time weather forecasts, right? So these are just some of the charts of what do different weather variables, how are they predicted. And it has predicted some of the hurricanes last year even better than the numerical models. So it's not just being faster, tens of thousands of times faster at the price of accuracy, but you can get both accuracy and speed. So, what are we doing? How is this possible, right? Usually it's a trade-off. Here we can do it because we are learning from data. So when you're doing a numerical solver and the traditional weather forecasts, you assume there is Navier-Stokes and you assume there's a certain Reynolds number. So you're making all these modeling assumptions and you're not able to train all of that with the data itself, right? You're not using the data to inform your modeling choices to a big extent. You can calibrate still a few parameters, but it's only few of them. You're not adapting the bigger set of variables to the data that is available. And this is what now neural-based models allow us to do. They can adapt to the data. And many times these modeling errors are huge. And that's why learning from data can help us get to better science.
Does that mean that there's some other underlying physics that hasn't been written down that's driving the weather that's not Navier-Stokes? Is it discovering some new physics? Is it more provocative way of saying it?
That's a hard thing to say, right? Because either Navier-Stokes itself is wrong. Again, there are papers of all kinds of edge cases where Navier-Stokes may not be perfect. Or the likely answer is you don't know precisely what is the kind of specification in the sense of like, what is the Reynolds number here and how does Navier-Stokes interact with? So the humidity
is off by a fraction.
Exactly. Temperature.
Chaotic.
Yeah. And it's also imperfect observations. You're looking at satellite data that is irregular. And in fact, in the global south, the predictions right now are much worse. You can barely predict over the next 3 to 4 days compared to in the developed world where we can do up to 2-week forecasts.
Because they don't have as many sensors.
Yeah, much less satellite coverage. So that is a big factor. But what these models can enable us to do is further adapt to maybe even limited regional data. You can have weather balloons or something low cost and further refine and learn from that data. And so this gives the ability compared to standard models, which are quite
Just
rigid.
to be clear, it sounds like mainly you're learning more precise data, not necessarily that the physics is wrong. Or
we're not decoupling the two effects, right?
No, but if it's learning something, it's making predictions different than what the pure equations would have said. Is that mainly because the data is different, or is it possibly because there's other things going on driving the? Yeah,
it could be a combination of both, and that's what we currently haven't decoupled. Meaning, it could be you have partial observations, so you've imprecisely specified your numerical model, and that's why it simulates it wrong. Or the equations that are being simulated itself are wrong.
Okay.
And I think in my view, it's more of the former because these equations have been stress tested in all kinds of wind tunnels. And it's mostly okay. right? But then if there are like all kinds of changes in Reynolds number everywhere in the planet and you don't know how to model that, you can make big errors because of those modeling choices.
Okay, let's get a question in.
In this class, we from the MBA program, so I'm thinking about the institutional take-up of these technologies. A lot of times in this class, we discuss how things are extremely disruptive. But as I look at this, you're looking at a traditional weather forecasting institution that has been able to uptake the technology that's 45,000 times better. Can you talk to me a little bit about how these technologies are maybe not as disruptive and how the improvements are taken up by existing channels without as much change? Or was there a lot of sort of internal shift in the community as this technology is taken up?
No, that's great. And, I think I alluded to in the beginning a little, right, how there was so much skepticism. And in fact, coincidentally, just before we released the model, there was even an opinion piece, can deep learning beat numerical weather models? And kind of the conclusion was, no, there's so much needs to be done, maybe years, maybe even decades before that happens. So I should say a lot of people traditionally who don't like the black box nature of machine learning were very skeptical, right? First of all, that it would do a good job because, you have rare events like hurricanes, right? You don't expect to do well on hurricanes. What machine learning tells us is to do well on typical events. Maybe weather like here in Stanford, good, every day is sunny. But it turns out that you can capture those events as well pretty accurately and sometimes even better than traditional models.
It could predict things it had never seen before? Like could it predict a hurricane without having seen a hurricane?
So it did see some hurricanes, right? So it's able to do better on that. And also we did some kind of even more drastic stress testing, like being able to put like a big blob of heat near the equator, which is almost unphysical because you can't just heat up just the ocean in some limited, and by I think 3 or 4 degrees. So we did these extreme tests, which hopefully will never happen on this planet. But again, what happened was something you expect. It kind of like the heat dissipated into other areas. Of course, it heated up other things, but it was behaving in a physically valid manner, even though we were giving it such extreme conditions.
And did you get much? I guess it's being adopted there, and to why it's questioned. Tell us a little bit about the resistance.
And so to kind of complete that story, we had the skepticism, but we were like, no, we should, we have the data. Anytime you give data to a machine learning person, we're just going to try and do it rather than debate beforehand if it works or not. And I think that to me was really the starting point. And once we showed that it's quite competitive to numerical weather models, there were other groups which again took up, just as we do in computer vision or language, right? It's never like one group. You suddenly see a lot of activity in the whole area, as well as, I was quite surprised, to be honest, like a traditional agency like ECMWF, as well as NOAA, which is
what does that stand for?
ECMWF is the European Center for Medium Range Weather Forecasting. And NOAA, which is the North American Atmospheric
Administration,
yes. Thank you. So both are using these models. They're heavily working. They're further, training on their own data, right, and improving these models. So I think I should say that I was a bit surprised how quickly they took this and employed it. But I think once you show them definite proofs, because we use the same metrics they did. It wasn't just, right, like one specific variable like wind or temperature, but even extreme weather events like hurricanes, typhoons. We documented a lot of the statistics of how well it works, and we talked to them a lot. So, this was done in collaboration with scientists in weather and climate community, and that also, I think, matters to ensure we do the right thing. Yeah.
Yes, I was wondering whether these neural operators should be viewed as accelerators for existing algorithms, or are they a entirely different class of algorithms? Or maybe do they have like the same computational complexity, or are they just generally faster?
So compared to numerical solvers, they're generally faster because the numerical solver, think of it as a special case of architecture within this class, right? And if you correctly chosen your architecture and trained it well, you expect it to be faster and better. And that's what we see in many areas. It's only the question is, what is the level of speed up, right? And the general rule of thumb is, if you have like numerical solvers that require a very fine grid and the phenomena is more nonlinear and unstable, we tend to get even better speed ups with these models. Yeah.
I'm a PhD student in computer science department. How does your model compare to say other models like GraphCast from DeepMind?
Yeah. So GraphCast was one of the models that followed based on what we do, right? So Graph is one way to think about, again, like looking at the relationship between neighboring grid points, and you can do that in a hierarchical manner. And so what we did was to like look at it, like treat the world as a sphere, and then look at, if I did Fourier transform on the sphere, right, its spherical basis, and learn the coefficients in that basis and combine them with nonlinear layers. So we're going to release an updated architecture where you can think of it as a hybrid that is both graph-based, like it has local connections, but it also has global information that still treats the geometry as a sphere. So I don't know if I had that here. I don't have it in this set of slides, but we can show the benefit of treating the world as a sphere and not a flat earth, not a rectangle, is if you make very long rollouts. So if you now not just try to predict weather for 1 or 2 weeks, but do that for years, right? So you need this for climate predictions, very long-term predictions. The model with the spherical geometry tends to be much more stable compared to treating the world as a rectangle, because at some point the predictions are no longer consistent, right? Because it's not constraining it to be on the sphere, and it tends to blow up and become unstable. And that's, I think, the other just high-level idea to think about when applying it to scientific domains. It's usually not one objective function. Even if I tell you the loss function is predict the weather in the next 6 hours and make that accurate, that's usually not good enough, right? With the weather model, you also want the ability to go longer term. You want it to be able to do extreme weather, which is rare events. So that's the difficulty in a lot of scientific domains. There are many multiple objectives, and sometimes you can't even define it as a loss function. So try to incorporate more of the domain knowledge and constraints to make the model well-behaved.
We have a bunch more questions. I'm just looking at the time here also. So I don't know if you will have more.
I can also, I'm happy to take questions. That's a more fun thing.
Okay.
And I can then quickly wrap up after. I just have a few more slides just kind of unifying this notion. So I'm not going to introduce much of new ideas. So
happy to do it that way, yeah.
I'm a CS undergrad.
Yeah.
I think you mentioned a lot of these different objective functions for different models. I just want to get a lay of the current weather modeling landscape, whether there's a bunch of different mixture of models for this specific use case or this specific climate, or something in the desert, there's a desert model. What does that look like right now?
I mean, right now it's a global model, right? It's learning across the globe, which we treat it as a sphere. It's learning the dependencies. So we're not, again, doing specialized models for different, say, geographies or different conditions. It's implicitly determined by all the variables. We have variables that describe the temperature, right? That describe humidity, pressure. So, implicitly what's a rainforest and a desert, but we are not doing anything further explicitly. Yeah.
On that same kind of thing, you have multiple models. Are you thinking about on certification? Can you validate them using one and maybe an adversarial model to kind of challenge it a bit?
Yeah, so this was the next thing, right? Talking about uncertainties. So there's different kinds of uncertainties, but it turns out, especially for extreme weather like hurricanes, the kind of uncertainty that matters is, what are my current conditions? So if you slightly change the path of your current hurricane prediction, right? The hurricane is still here, in the Gulf of Mexico, and then whether it's going to hit Florida or make landfall, how do you predict that early on? As early as you can predict, the better. But of course, if you start early on here, as you see from the Gulf of Mexico, you slightly perturb it, the predictions can change vastly. Because this is what we call chaotic phenomena. If you've seen the butterfly effect, either the movie or heard about it, right? Very tiny changes can have big effects. And that's the other challenge with this, right? Compared to standard vision models where you have lots of robustness, here this can be quite delicate based on making even small changes. But what we care about are these uncertainties. So not just give me a path of where the hurricane is likely to be, but the sensitivity, if I now slightly perturb my current condition, how much is it going to change? And that's what will help me determine what is the probability it'll hit Florida. And based on that, I can take action. I can be like, oh, should there be an evacuation? Should we plan for certain reinforcement of certain kind? And that's where these models are much better than traditional weather models, because I think you'll be surprised. If you look at the traditional weather models, can you guess how many ensemble members, meaning how many such perturbations are done to determine sensitivity? Want to take a guess? What is done today, right, in the actual ECMWF for these? You think only 10?
I'd be surprised.
50. So it's not a lot, right? If you ask about standard deviation of 50 numbers, right, just 50 samples, no, it's not really good. And of course, if you do
Why
that,
do they do so few? Is it expensive to do more?
it's that expensive because each one requires this big supercomputer. And then, all governments have limited resources, and we have, and whereas with these now models being so cheap, you can run them in a single GPU. Now you can do thousands or even millions of samples, right? So you can get to the right statistical bounds as needed. That's no longer a constraint that you have to limit to just having 50 scenario runs. And when it comes to climate models, in fact, it's really bad. Many of the climate predictions you see is a single run. But what is climate? Climate is like saying what happens in decades, right? So you cannot just do one run and say what's going to happen. You need lots of runs. And this is where bringing down the cost has an impact in making that uncertainty quantification much more precise.
And the extreme values may be more important than the median.
And that's why the extreme weather, this is so important. If you don't have enough of the spread, you miss the extreme events. You can't even predict that there will be an extreme event. We've shown this not only for hurricanes, but also heat waves and all kinds of extreme events, that you can capture it once you increase the number of ensemble members.
Right. If your hand is in the freezer in the oven, on average, it's fine, but you could
exactly. You need to kind of have the spread.
Yeah.
Whoever.
Hi. Quick question. So I'm studying economics. I'm really fascinated, obviously, by what you were talking about with both the work you're doing on genomics and viral and bacterial mutation prediction. My dad is a virologist, so this is all really crazy to think about. I'm wondering your perspective coming both from industry and academia. How do you see academics viewing this new technology? Do you feel like there's an openness to it, or is there kind of old guard, new guard tension? Are they embracing it? How is that looking?
Yeah, I mean, it's similar to what I mentioned about weather models, right? But it's funny. I think biologists are a lot more open than physicists. But that's changing fast. But I think maybe because biology, there's even less of a rigidity of, I know the model. No one really knows, right? Sure, you can posit something at the level of molecules, what the forces are, but try to get all the way to anything that is at the human level or clinical level. There are just so many levels of uncertainty, and it's clear that the more data we can get at all these different levels of experimentation, right, the better we can be in terms of prediction. And so there's been a lot of interesting uses. In fact, not this genomic model, but some of the other techniques we've done in speeding up quantum chemistry as well as the binding process. It's been used in a drug that is now getting to clinical trial in a startup that I helped advise. and help start that venture. So this is now kind of really going into the real world as we speak. And I don't think academics are anymore debating whether to use it. The question is how to use it in a way that still satisfies some of the requirements you have for traditional methods. If we have certain checks and balances to say that traditional simulations are doing well, we want AI to more than satisfy it, right? If it fails those, then it's not good. So you still want that, but do better than what's been done before. Yeah.
How much does the quality of data that's put into the models matter? And how do you ensure the quality of it across the world?
Yeah, no, that's a great question. And in a way, we are in a better world than language models, right? Language models, you're just beholden to whatever is on the internet. You try your best to curate, and you've seen over time models that have done better data curation, even small models have gotten to very good result, including the Microsoft Phi model, the Phi series. And so data quality certainly matters. But here, we're talking about curated data in lots of ways, right? So the biobank for the genomic data, these are scientists carefully curating it. Even the protein folding, that was successful because it's scientists over decades carefully creating that database. The weather data, all the historical data, that is taken from the satellites, but further what we call reanalysis. So it's further using the models of physics to complete the grid and remove the certain biases because satellites are not uniform coverage. So we are in, and of course, any kind of other simulation like fluid dynamics. And so you can generate from existing numerical solvers. So we are in a better world because even though it's smaller data, it's very carefully curated, cleaned up data, having experimental validations, right? For the weather models, all of this data has been carefully checked with actual real world predictions, right? So any change you're making there requires a lot of thought. And so we are in this better world with small data, but much higher quality data. And we also have laws of physics in different ways that we can use and be creative about it. Yeah.
And I'm a senior majoring in political science. I'm curious, as we see the next generation of GPT-5, GPT-6, what do you think are going to be the next type of frontier problems that we're going to be able to solve that we aren't able to?
Well, agents, right? So it's very clear they're doing agents, and there's also some online chatter about a new model and how that's able to do more reasoning and
like Q-star.
Yeah. Well, the GPT-2. In the LMSys, they call it GPT-2.
I thought that was kind of a joke, no?
But it does solve some of the problems, like a math Olympiad problem it was able to solve that none of the previous models were able to do.
Okay, we'll see.
We'll see. I'm not speculating.
But Jan LeCun was saying that they were just memorizing some of those.
Yeah, I mean, Jan LeCun is skeptical, and many times he's correct. So again, I'm not.
We'll find out soon.
I'm just repeating the gossip without making a judgment on it.
I don't disagree. The two trends, the agentic and then reasoning and stuff. Yeah, I don't know about GPT-2.
Yeah, and you can, right now it's no longer about a lot of additional data, but really this repeated interaction and alignment, right? So you can try to reinforce the model to do better on certain tasks by looking at repeated interactions and giving a reward function that, you want to solve the math Olympiad problem in the very end that has a lot of steps. So it's no longer just trying to make one step of your interaction to be good, but do it over a much longer range. And that's computationally very expensive, but OpenAI has compute, so we are in that. I want to come
back to this question about data and theory, because it's very fundamental to everything you're doing, and we talked about it a little bit before we came down. So Rich Sutton has this bitter lesson, a simple idea that more and more data, and I saw Andrej Karpathy, and we were talking about how Tesla was getting rid of hundreds of thousands or millions of lines of code, replacing it with machine learning. And I think you and I were talking about in language models, how they used to have rules of grammar that were very important. Chris Manning and others had, and now it's just statistical.
Yeah.
So that's all in one direction there. But it's more complicated than that, because you're showing that if you add some theory and some, sometimes put some constraints on it, then you can work with much smaller amounts of data and get reasoning. Can you say a little bit more about that? Is there a broad arc towards just more and more data and less theory, or is what's going in the other direction, and how should we think about those trade-offs?
So I would say that you need to be very creative and nuanced in terms of adding theory or structure into the models, right? So it cannot be done in a very rigid way that limits the expressivity of the model or the ability of the model to really learn better features based on data. So, the thing is, if you have enough data, always go with data. It should never be at the expense of data you impose some structure. And that's where I think a lot of the previous failures were. Because in language, yes, you can try to do a syntax tree, but it's not always perfect, right? Especially on the internet, people use language in all kinds of grammatically bad ways. So you don't have a rule that is perfectly met. And also, if you impose this, the optimization landscape can become much harder. So even if it's perfectly correct for a certain domain, you cannot learn it because you've imposed a condition that is too harsh. And same with our models. The thing is, we have the flexibility. It's similar to a transformer, but put into now a continuous domain. So it can learn anything. If it's given enough data, you don't need to add any further structure. But because the data is limited, adding the structure that kind of aids the data, right? It's complementary to the data and still can learn well. I think that's why it's a little bit more of an art. And you have to be careful. So most of the time we just start with data. In fact, in the examples of whether we only use data, right? The only nature of physics was assuming it's a sphere and making that constraint, right? We never kind of carefully went and tried to do a conservation law of physics, or that, where the temperature, how does that move? We never. Although there's a little bit of, when you're describing satellite data, I guess they're using some physics to fill in some of the gaps and smooth things. Yeah. So even maybe in curating the data. Exactly, but it's implicit. We're not explicitly saying we should always. And explicitly imposing that is the hard part, because optimization gets harder if you say no. Well, what if when you get the data, there's some kind of data point that just doesn't make any sense? Does your model try to smooth that over, or does it try to? I mean, as with any deep learning, if it's only one data point, it usually tends to get ignored, right? If it's enough data points, it tries to pick up the structure. And that's why if you think about hurricanes, it's quite anomalous, right? You have this hot and cold air like mixing in a weird way. That's not normal condition, but there's still enough of those signatures, even if it's a few of them. It's interesting and different enough that it picks it up. Because the model has the flexibility. We are not constraining the model to be rigid enough only to have like smooth air flow. We are allowing it to capture that. And the other thing, when you're talking about the DNA, the viruses and the protein folding, I mean, there's really several different theories there about predicting the next word, but also the going from the sequence to the structure of the protein and how that folds, and ultimately to its function. And each of those steps, you're kind of chaining them together to get. Is that sort of related to the agentic world, but having a bunch of these systems connected together that each feed to the next one. Is that what we're going to be seeing more and more of? Exactly. And in fact, that's what we did in the follow-up work to that, where now you can give reward function instead of the human feedback. For language models, you can ask a human thumbs up or thumbs down, did it produce something that you liked or not? And that's how you do RLHF. And now instead, the reward function here is, does it bind well? Give me something, for instance, based on molecular binding simulation, is having a certain binding functionality, right? Or does it fold well? We don't want disordered proteins, right? We want ones with good structure. So all of this you can give as reward functions, and you can do reinforcement learning, or what we also call direct preference optimization, which was actually developed here at Stanford. So these techniques we can now use, and we can chain both models that produce discrete sequences with models that have predictions in the continuous realm, like binding, for instance, and bring all that as AI models, make it fast, but also have the ability to differentiate through that and come up with ultimately good functional proteins, which is what is a huge impact in real world. Great. Let me just I'll I'll just maybe, there are other use cases. So this is carbon dioxide storage. I won't get into the details other than to say you can simulate, if I pump carbon dioxide to these underground wells, how do I measure the pressure buildup? How do I predict how the carbon dioxide, where it's going to go over several decades? Will it stay within the well, or will it just diffuse off and go back to the atmosphere, in which case we don't want to be doing this, right? So it's helping us plan for a net zero future. And again, work done with collaboration here at Stanford with Sally Benson's group. I know I keep coming back to Stanford in many of these works, which is great. A lot of great collaborators here. And so many domains, material deformation, nuclear fusion I had mentioned earlier. This is like in the tokamak, how do I predict how the plasma is going to evolve? Where is it going to be concentrated? Will it try to escape? I can look at the camera data as well as the magnetohydrodynamic simulations. Imaging. So, imaging, you want to look at an inverse problem. You look at just waves that come out and at the sensor, but what you want is what is inside the human body. So these are inverse problems that you can do much faster. So the other thing I just want to emphasize is not just trying to think about simulation or prediction, but inverse design, right? Can I generate better designs? So if you ask DALL-E or any kind of image model to draw an aircraft or a drone, it draws something, but probably meaningless. You can't go physically manufacture and do anything with it. So here I've shown two examples. One is a medical catheter that we designed at Caltech. And the idea is, in a standard medical catheter, it's just a tube that draws fluids out of the human body. But the bacteria tend to swim upstream near the wall because there is less velocity of the fluid, and it tends to infect the human. In fact, more than 500,000 cases of these healthcare-related infections, the top one in a hospital. So if you're long enough in a hospital, unfortunately, you tend to get infected. And so we had a very simple idea, which was to build these ridges or triangular shapes within the catheter, very tiny, something you can 3D print, but optimize for the shape of it. And what is the intuition? With these triangular shapes, what you can create are vortices. So, the fluid, because of this sharp shape, it kind of becomes like a vortex. And then the bacteria is not able to swim upstream because of that disruption. And what you see is the 3D printed version of the catheter down below, where the particles that are moving in the fluid flow means they're not able to swim against the fluid, right? So they're not able to go into the human body. And we measured 100-fold reduction in bacterial contamination. And now it's in clinical study, very fast amount of time. The AI proposed a design, we 3D printed it just once, and it worked. Right? And to me, that's the message I want to give. A lot of the experimentation could be potentially removed with the use of AI. And of course, there's always uncertainty. Something, if you cannot model very well, you would need the physical experimentation. But you can further adapt your model based on that and make it progressively better, so you can hopefully do less and less experiments in the lab and do it much faster with the use of AI.
And this is an early example of just a complete revolution is going to happen, where we don't just make these, fantastical images of houses and bridges and, catheters or whatever that are very pretty or creative, but ones that actually work, that don't fall down, that have functionality.
Yeah. You bring them to the physical world, right?
And then you can print them, you can create them, so start making the machines that actually work.
And the other quick example of that is optimizing for mask design in lithography, which is in chip manufacturing, again, very important part of especially the latest GPUs. As you go to smaller scales, this aspect of physics, the diffraction effects, become so critical. You have to get the right mask design. I won't get into it, but again, this is an inverse problem that can be done. But where does all this lead, right? So far, I talked about lots of use cases of science. And mostly I talked about models that learns on specific data of a specific domain. But ultimately, what we are thinking about now is a model that could one day understand all of science. In a way, you could say ChatGPT understands all of science, right? Because it has read all kinds of textbooks. If we ask it a question in any domain of science, it does a decent job. If you ask it to design a molecule, it could even do some of it. In fact, we did that for some of the direct air capture. It does some suggestions of linker molecules. But on the other hand, if you ask it to actually simulate and predict if the molecule is going to bind in a certain way, or the weather model will, or what would be the weather tomorrow, it can't internally simulate the physics. And if you look at models like Sora, it learns on lots of videos, but physics is almost an accident. Whatever video showed physics, it kind of learns it. But can you ground all of them with physics itself in a direct way? And that's where now we've trained roughly a GPT-2 sized model, which involves now training on multiple different kinds of physics, fluids, wave equations, material. So think of like a model that now learns to simulate and design on many such phenomena. And not just a simple kind of physics, but one that could be even multi-physics. If you're now thinking of an aircraft, it can be both looking at aerodynamics, but maybe you also don't want it to be having a lot of sound, right? And it's also the material stretching. If it's high temperatures, you don't want the materials to stretch. In the real world, physics is not isolated into one equation. It's lots of equations to describe something very complicated. And weather is one such example. It's highly multi-physics. You're not just defining it with a very compact, simple equation. And so ultimately, can we have a model that can learn over lots of such coupled physical phenomena and get to a better physical foundation for all of AI? So to me, I think that's an exciting future.
That is very exciting. Well, thank you very much, Anima.
Thank you.